Okay, let's start. So today we start part 2 from this plan I set in the beginning. This will be about infinite Galois theory. And thematically it has nothing, not much to do with the previous 2 lectures, previous 2 days. The connection will come at the end. So we have the following general situation. Quite easy. That this is Galois extension. But we don't assume finiteness, so possibly and actually it will be interesting when it's infinite. So example, and then we want to understand the Galois group. And get the correspondence between some subgroups of this group, and sub-extensions here. So it will be a bit different than in usual case, because not all subgroups will be allowed in Galois correspondence. So example, to have in mind, I suggest that there is some prime number doesn't really matter which one, the structure will be the same for all, and then K is field of P elements and M is its algebraic closure. So this is finite, this is infinite, so extension is also infinite. Okay. P-adic numbers will appear here, proofer not so much. Similarly, similarity to proofer may be that it is this union of all Fpn. Similarly as proofer is union, but proofer is increasing union. This is not increasing, as I will say. So in general, it may appear later. So if F is a field, then F sep is the separable closure of F. The set of all separable elements, so all elements from algebraic closure, which are separable of LF. And then we have something called absolute Galois group. So it's just one field here. Which by definition is the Galois group of the separable closure, which is then Galois extension, because it must be normal and it's separable by definition over F. Okay, so always we have such a thing. And actually such groups will play an important role in our model theoretic description of actions of finite groups. Okay, so this is just a notation, maybe confusing, but we really mean all automorphisms of separable closure over this F by this notation. So in this case, Fp alg is the same as Fp sep. That's probably you know. Fp is perfect. So all algebraic extensions are separable. So this group we are interested in is the example of this absolute Galois group. So my point is that this example we should have in mind. It is also an example for something else, for absolute Galois group of this prime field of P elements. Okay, and so this group we will fully understand, and in general I will give some description what is the necessary extra structure to understand such groups.
I was saying this Galois group is, I was thinking it's P numbers.
No, but something like this, like all, we'll see soon. Okay, so, yeah, no, actually, no, it is confusing. This P has nothing to do with this group. For all P, it's the same group. Okay, but it is pretty confusing. So no, so actually the answer is rather not, because it's really, this group is unrelated to P. Okay, it's related to the situation that we take finite fields, but actually for any finite field, its absolute Galois group is always the same. Okay, which we will see. Okay, so now this technical part starts, which requires a bit of patience, but so as in your lecture of Galois theory, you usually consider finite Galois extension. So we'll understand this infinite one via the corresponding finite sub-extension. So for this as above, consider such a thing which is called direct system, but this I don't want to define very precisely. Okay, possibly. Where this is finite and Galois. So indexed by something. So all. Yes, so this is system of all finite Galois sub-extensions. Okay, such a thing. So actually the system will come to play to understand this group. So in the example, okay, this is abstract, but then always you should have in mind what does it mean in this particular example. In the example, all these ki's must be f to the p to the I finite is. So in the example, this is fp, fpi inside fp alg. So only this is changing, of course, this part is changing. But I'm just writing where is it. Yeah, so this is some field inside, but close to this one. This will be probably still infinite. This is infinite. This is finite and Galois. So in this case, it ranges over all, let me write like this, positive natural numbers. Okay, and now we can order, so there is some indexing set which can be ordered by inclusion of the subfields. So here, so we put an order on I such that I is smaller or equal than j if and only if corresponding fields. Okay, so then this becomes so-called poset, which is partially ordered set. That's a short name. It's actually directed with any, of course, if you have any two fields. So not necessarily two fields are comparable, but any two fields are embedded into the other, which is finite. So again, always look at the example. In the example, that's the another thing which is often confusing. So we know that I is n plus, but the order is not the usual order, it is divisibility. So Fi, Fpi is a subfield of Fpj if and only if I divides j. That's the rule. Yeah? Not if it's smaller, if it divides. So here, this is divisibility order. Yes, this is not increasing. This is not increasing union like here of these fields. One is included into another if and only if this exponent divides the other. Okay, so that's example of the order. But now, if we go to Galois groups, so again, we are looking at this situation. So now, this becomes, which I will define soon, an inverse system. So don't worry, definition will be given soon. Inverse system of finite groups. What does it mean? So we have for each I and j in I, if I is smaller or equal than j, then ki is inside kj, so we have restriction map. Just takes automorphism, some sigma here. Okay, one can wonder whether it preserves Ki, but it preserves because it's normal. If you remember this property that normality of the extension is actually equivalent, that all bigger automorphisms must preserve this as a set. So this is well defined. It is here because Ki over K is Galois. Otherwise it could move it to some other field. But because of the assumption they are only Galois, this is well defined. and it's actually onto. Huh?
Since all the groups are in Ki.
Yes, yes. That's the argument. So it comes with the system of homomorphisms. It's a homomorphism, yes? If you restrict and compose here, it's the same. Okay, so now we are getting more and more structure related, all these finite groups, but now also with respect to this order, but in another way. Here I is smaller than j, and we get from here to here. We have maps going the other way. And also, for any I smaller than j smaller than n, if we first restrict here, just a restriction of restriction is like one big restriction. So it's not much to say.
Did we assume that I is directed?
So it is by, yeah, that's what I said. I just said it because of the nature. It is a conclusion of the situation. Okay, because if you have, as I said, if you have any two fields, finite, yes, but still I will say finite Galois, then the composite is finite Galois and of course contains both. So it is directed in this case. Okay, but actually the definitions I will be giving will also work for non-directed systems. And okay, I don't think it will be important. Maybe it's okay, I'm not sure whether it will be important at some moment, but it is directed in this case. So this commutes. So let me just write it. Okay, and of course, restriction to itself, it's just identity map on this gal. So basically such a thing, abstractly, is called inverse system of groups. So now I will give definition. So there are like three levels of generality. We have this general field extension, which produces such a situation. We have particular example to keep in mind. But now I'm generalizing this situation of the systems of groups to any groups, not necessarily Galois groups. Okay? So an inverse system of groups. Okay, and if you know what the word means, it will make sense in any category when you have the notion of morphism. So I'm saying of groups in category of groups. Okay, is a collection of groups so some people assume it is directed, but I think it's not necessary. So indexed by a partially ordered set, so poset such that this happens. Okay, and no, so together, not only that, so together with these maps, together with group homomorphisms, R, J, I for all I smaller equal than j, of course, coming from this indexing set. So Rji is from Gj to Gi group homomorphism such that the same happens. So
restrictions are onto, right?
sorry?
These restrictions are onto.
Here are onto, yes. Here are onto. In general, they don't have to be, but then we can change system to one which there are onto. Just taking so. But here they are, yes. So such that for all I smaller j smaller than k, they are like restriction maps, but now they're abstract. That means it commutes, and from I to I is identity. Okay, so any infinite Galois extension gives us such a system coming from finite Galois subextensions. Okay, so now let's see some examples of this abstract situation, which actually will be the one isomorphic to the situation from particular example, but this we will see slightly later. So example, yes, so always Ci, this will be cyclic group of I elements, and then if I divides J, we have this actually epimorphism such that generator goes to generator. Yes, you can always map epimorphically one cyclic group to another. I mean, if only if the order here divides the order here, and if we arrange it in proper way, this gives us, and this becomes C Rj this is inverse system of this finite cyclic groups. This is example 1. And we can also restrict it somehow, and then we get PAD. But okay, better to call it Q for some reason. Now let's fix another prime. Okay, so here again we have n plus, and the order is divisibility, like there. Now we can restrict ourselves to only powers of Q as i's. Then consider, then we have CQI. This is also inverse system. But now this is with the actual, yes, of course, any Qi divides Qi plus 1. So I'm taking like part of the system, but these i's are powers of Q. That's another example. So this is inverse system of cyclic, okay, I may say cyclic Q groups. And so power of, okay. So maybe, okay. So now we can combine it with the previous thing. Okay, so another example. Okay, example A, example B. Okay, so I also hope that you know that the Galois group of FPI over FP, it is cyclic and generated by Frobenius. Okay. My notation is like this. So if K is a field of characteristic P, then Frobenius takes A to P.
P to the I is that I.
Sorry?
It's isomorphic to C P to the I.
Yes, yes. So it has no, CI. CI. P doesn't matter. P kind of never matters. That's yeah. Somehow that's a good thing to have in mind. In this situation, really, P doesn't matter at all. Okay, of course, its characteristic is P, etc., but Galois theoretically it's like invisible. CI, yes. Because this I has to be dimension of this space, So of course the dimension as FP vector space is I.
Taking I times Frobenius will be identity.
Yes, what to do to the I. Okay, but also if I divides J, then actually we have a perfect, because here it was a bit strange generator to generator, but I didn't see exactly which generator. And it must be a good choice of generators, so this condition is satisfied. Okay, they really have to go in compatible way. But for example here, they do. If I divide J, then we have the restriction map, Ji FPJ so we know what they are. So here we look at generator, but now we have Frobenius on bigger field. But it is just raising to power P, so if we restrict it, it's still raising to power P. Okay, so it goes to, of course, Frobenius. So we see generator goes to generator. Okay, so this, in this case, this inverse system is exactly this inverse system up to natural isomorphism. Okay, so the inverse system Gal FPI FP. Okay, I will not. It's isomorphic. Let me not define it formally to this previous one. Yes, so there are isomorphisms between all these groups, but also the corresponding maps goes to corresponding maps under this isomorphism. So now Okay. So now the question is, what is a connection? What's connection between this big group we want to study? So now we are in this general situation of the time Galois infinite between this group and this inverse system of groups. Okay, so that's the question, which will be soon answered. So the answer is that we always have a big restriction map. Okay, so we have, okay, so for each I in I, we have like a big restriction map. Those were like small ones from finite extension to finite, but there is also a big one from this big to each of the smaller ones. I mean the same. Which has the same property, I mean the same, similar like here. Okay, so unfortunately there are several of these diagrams we have to go through, so such that for all I smaller than j, such a diagram is commutative. This is this one smaller restriction. Okay. And this will be part of the definition of inverse system, or of inverse limit of an inverse system. So the definition is
I think we need to have something like union of all ki's is equal to m.
It's not really, this will be related, it is true of course, because if you take any element in M, it has some finite, it is a root of a polynomial, so it lives in a finite Galois extension, just take roots of all roots of this polynomial. Okay, and it will be, I think it will be not visible that we need it, but one problem I'm giving you probably will have to use it. So really the fact that this is the inverse limit, which I have to define first.
Did we take M over K as an algebraic extension, right?
Algebraic Galois extension. But, yeah, Galois means algebraic.
By the Galois you mean the automorphism group, right?
Huh?
By the Galois you mean automorphism group.
So yes, this is always automorphous group of this fixing K.
For infinite,
The same.
okay.
The same. So it's always algebraic. This has the same meaning, but it becomes infinite. So that's the problem, that then it's harder to understand. So that's why I have to talk about all of this. To understand this infinite group, where is it, this one, actually, topologically, it will get some topology. And with this topology, it will be like really full structure for the Galois correspondence. So some work is necessary to describe this topology, and topology is described via this inverse systems and inverse limits. So all of this comes together, and I think at the end of the lecture today, we will see the full picture. Okay, but you should have in mind, okay, there are many these finite ones. So the best example is this FP alg, when there are these finite subextensions corresponding groups, but then goes the other way, like this inverse system of cyclic groups. So this is like a very simple situation, really, because it may be much more complicated. So it's always, if it's infinite Galois extension, it's always quite complicated. There are lots of these things going on. Okay, so still I should give formal definition what is the limit, because this connection will be that actually this is the inverse limit of this system. So we have to know what it means. So an inverse limit of an inverse system. So I'm not always writing these maps Ri, but they are always there. Is, of course, of groups. But the same definition makes sense for in any category again. Is a group G together with a collection Ri, Gi of homomorphisms such that two things happens, one like this, but this is not enough. There is also very important universality property. And because of this universality property, the proofs get pretty long. So first condition for all I smaller than j, exactly this happens. So Gj, Gi commutes. Okay, but it's not enough. Second thing is, and this is really long, that for any other candidate satisfying this, there is a unique map from this other candidate to G, commuting with everything else. Okay, so 2 is called universal condition. So for any other group, with maps Ti so such that again this holds, So this is like another candidate. Kind of this one says I am a better candidate. So there is a unique phi from this H to G such that for all I in I, this commutes, this unique one, okay, so that's pretty long. Yes, so first property says there is this general map to the inverse system as in this case. And second one says if there is any other candidate with such maps, then it has to be kind of above this G. So now I'm telling you to check in a problem that you are exactly saying we don't know, but we will know in maybe 10 minutes or 20. but still, okay, I'm maybe catching like several birds at one stone, because this definition again makes sense in any category. And in any category it may not exist. But the problem says if it exists, it's unique. It's unique up to isomorphism. So this is actually true in any category. Okay, so if inverse limit exists, it is unique up to, which is actually quite easy by this universal property. That's why. And then notation. G equals such an inverse, arrow going to the left. You can write here I in I. So still I'm skipping all these maps Ri, Rij, which sometimes we may put here, means that G is an inverse limit of sometimes inverse limit people, but in more general category, they just call limit. And okay, there is also notion of direct limit, which is sometimes called colimit. But we just are interested in inverse limits of groups. Okay, so finally, keep this. Another problem for you, where probably it is used what you said, that M is the union of Ki, is to show that this is inverse limit of this system. So this is the connection. Okay. It still doesn't maybe explain so much, but then, okay, so maybe I just state theorem and then make a break. So general theorem now that they exist. But it will be also important what is the construction of this general inverse limit, because from this construction we will get a particular topology. And this topology will be used here. So this will be this full circle of connections. And this is general for any groups. So let this GI be inverse system of groups. So now define curly G as elements of products of all of them. Yes, this is Cartesian product. Not a direct sum, Cartesian product, so all elements are allowed here always, which is a group as well, such that they are mapped to each other with respect to these maps Rij. So such that for all I smaller than j, Rji maps the jth one to the ith one. Yeah, so this is like, what's the word? Like threads, like this infinite product, I don't know here, but here they are mapped next to each other from this product by these connecting maps. That's the idea. Very, very, very long sequences, but not arbitrary. Elements are mapped, coordinates are mapped to each other by this Rij from the inverse system. Okay, it's also maybe a bit hard to visualize all of this. So everything is infinite, these infinite sequences, but connected to each other by maps from the system. Okay, then easy to see that G is a subgroup. So it is a group itself, and here we have always projection maps to ith coordinate. Okay, and here we have just Ri is the restriction of pi I to this special subset of the sequences. So the statement is that then G together with these Ri's is the inverse limit of GIs. So this is general construction which always works. Okay, so this I plan to prove, so let us do it after the break.